What is so different about physics versus machine learning, right? Like, why is there even a versus? So here's where my story starts. So I'm Aruna. As I already told you, I started my adult life with a PhD in theory physics, and that was the lowest point in my life. After that, everything has been relatively high. So I've worked in machine learning for about 20 years after my PhD. I'm very old, but after that, I was in Google last, where I left Google around September, October last year. And since then, I'm doing lazy things, trying to figure out what next should I do, what should I start, what would I do with myself. And in this little informal session, I'm just going to talk through how I came into machine learning from physics. So I'll start my story, from kindergarten, which is sort of PhD for us. And, how I grew from there, what was surprising for me in machine learning coming from a science mindset. It's slightly different. I'll tell you the commonalities and the similarities. And I'll tell you a little bit of what was useful for me coming from a science background, and then how I built, whatever you can call a career so far, using that to some sort of an advantage, relative advantage, and where I've gotten more into business and formulating the right problems or the wrong problems, but doing it myself and then trying to solve them. So that's what this talk is going to be about. So it's largely a story. I will gloss over the technical details, the hard parts, but you can stop me and ask questions, or I'm happy to talk about them later too, to the extent that I know. Okay, so here's where my story starts on what is so different about physics versus machine learning, right? Like, why is there even a versus? And I heard this in a little talk by Noam Chomsky when I was doing my grad school, and that's very old, when Noam Chomsky was still sort of relevant. And, and he said that there's nothing new under the sun in machine learning, because obviously he's Noam Chomsky, but then I liked some part of what he said, and it opened my brain on why did I find machine learning so hard. Like, it was not that the math itself was hard or the techniques were hard, but it just was very hard to understand why this thing worked, why is there such a big fuss about it, and I'll tell you why, right? So the way I got initiated into science was really thinking deeply about things that happened around you, right? Which, we were told that white men did. They sat under trees wearing wigs, and then an apple fell on their head, and they figured out gravity, right? So that was sort of the inspiration for all physicists. And we were told that if you ever used a computer to figure out things, you were clearly not smart enough. Like if you read Chacha Chaudhary, your mind is supposed to work faster than a computer. So you're supposed to sit out there under the sun and think and solve problems, right? So that's how we got told we should be solving problems, formulating problems, and that's how we started. So, someone sees an apple fall, and then they're thinking about different apples are falling at different time points. Can I really infer something about why this is happening? And, let's say you're not Newton and you're rediscovering this problem. You start with assuming something pulls the apple down. And what might it be? Is it intrinsic to the apple? Is a heavier apple falling faster? Is a lighter apple falling slower? And you make all these sorts of observations. And then you go about doing something called dimensional analysis, which is basically you say, I'll make up an equation where the left-hand side and the right-hand side have the same units. If I'm measuring time of fall of the apple, then it should be somewhat related to something that has the units of time, like that, And this then holds true for pendulums. It then holds true for anything that is falling under the influence of gravity. And now Noam Chomsky said that if you were a new age scientist, you would discover Newton's laws like this. You would go about fixing, a trillion cameras across a trillion trees, apple trees, and then you would let these apples are going to fall over a long period of time, and then you're going to record a frame every, say, 1 femtosecond. And you're going to store this, and then you're going to run very large compute on this just to predict when the apple will hit the ground, and you're going to get it right. And that very large model will now become a foundational model of gravity, right? And then everybody will build on top of it. That's not what Noam Chomsky said, but I'm paraphrasing for large foundational models. So this pretty much becomes foundational in machine learning. And this was very hard for me to think, why would you solve such a simple problem in such a complicated way? That's how it appeared to me. So this is how computer scientists were solving problem, they were looking for some sort of an algorithm, which is a different way of thinking from some sort of a model. Like when you're looking to understand how things work with building a model, you're kind of trying to abstract out how it functions and trying to say this must be the inner true property of it, somewhat very Indian, I felt. And then if you're more, if you're more towards the practical side, you're like, I don't care anything. I don't care about this. What I actually can see is the time of fall, and I'm just going to compute that. And it took a long time to see this difference. And this is how I think smarter people have classified it as the difference between doing science and doing machine learning. Okay, so in science, you're observing something, say, as y, and then you have a set of input variables you're observing, say, x, and you're trying to look at how should y be related to x. It could be time of fall, it could be time period of a pendulum, it could be anything else, right? It could be what comes next in a sentence. You're trying to model, like I said, you're trying to do some sort of mathematical model between the input and the output. You like symbolic thinking, so you think that if you come up with that equation or some framework for it, then you have some model of the underlying system, right? Whereas in machine learning, all you're saying is, I need some algorithm that computes it. It's okay if it's a bunch of if-else statements. It's totally okay if it just, that's how pretty much 90% of large enterprise code is, so it's totally okay. It works, runs a business, so good enough for me, right? And then in science, the other thing that you do quite a lot is you try and minimize the number of parameters in your equation or your model. So you're saying, let's say, even if you have linear regression or logistic regression, what you do is you'll keep having, if you don't do it, you'll have your co-students, your professors asking you, but why exactly do you have that in your equation? What does it matter? If I was in Las Vegas, would I measure that? If I can't, then why is it there, right? So you keep trying to cut down what we call reductionism, and you keep trying to form some sort of minimal set of parameters to describe your system. And that's how you do science. It's true in biology, it's true in chemistry, it's true across natural sciences, right? And then you check for repeatability and universality of what you found. Like whatever you found with a pendulum should be replicable everywhere across the world. There's a reasonable human being who can figure out how to make a pendulum, right? Or look at apples. So it should work across. Whereas, in computer science or in machine learning rather, which is not the same as computer science, so I apologize for that, but you're okay to have multiple different algorithms compute the same thing. I might write if-else statements in a bad way, you might write it in a good way, you might never go to your else path, that's totally okay. Your model and my model both work, and both are equally useful for computing something, then I accept both as valid models of the thing I'm trying to compute. And it's also okay to have hundreds and billions of features. As you know by now, it's totally okay to model language as containing 2 trillion parameters. If that means you can talk better than a 2-year-old, that's totally fine. Whereas a physicist or a scientist approaching linguistics, it would be totally a no-no even if you had 20 different ways of making up a sentence. Then you would get told you probably don't understand a sentence very well. Think about it and try and look at one nice thing you can say about a sentence that makes sense. So you could imagine why people came up with things like subject, object, verb, how linguists and statisticians try to approach this from a reductionist sort of way rather than just go crazy, use every word in the dictionary, keep remembering when it came, where it came, neighboring words, everything, do whatever you want, but make a sentence right. So this was sort of the, I would say this was my dissonance with machine learning when I entered the field, maybe 20 years back. And it was very hard to understand why are people using so much compute. And I used to think that of all sorts of power that's most abused in the world, it's not political, it's actually computational. Because people are just going crazy with, and GPUs were a thing then. I even used it in my thesis. And they were really expensive when they came out. And it looked like, why do you need a GPU to tell something that's so simple? You really should think harder, right? So this is how I started. So I'll start with my kindergarten, which was really a PhD. And I'll tell you what problem I solved. And I saw computer scientists who bought me coffee solve. And they were paid a stipend to do it. So obviously, I understood what the world valued more. But I wanted to understand how do I become like that, right? So I found someone in Urbana-Champaign, where I did my PhD, working on similar problems. And I'll tell you what that problem was. It was basically a protein folding problem. And I'll tell you we were interested in it in different ways. A protein starts out as a linear chain of amino acids. Stop me if that doesn't make sense, but just think of it as a sequence of beads strung together. And when it's made, your DNA RNA system codes for it. When it's made, it looks like a linear chain, something like that on the right side. And depending on what beads that chain contains, it goes into a 3D form, which is more complicated, looking something like the folded state last, which determines how you live, how things happen. If that goes wrong, you might not have muscles. So that's a muscle protein. It's called vilin. Basically, it lets you fold your hands or works on your joints, help your muscles contract, expand. And it's very important that it come to this exact shape, and you have about less than a millisecond for that, for it to be active. And you should be able to do this repeatably, every time, every second you have so many thousands of proteins born and dead and doing little functions. And this is something that, biologists and physicists were very interested in, on how does this happen? Like, why does everything that why do all our body proteins fold within milliseconds? And except for very stray cases like Alzheimer's, Parkinson's, they mostly fold correctly. And only very few proteins fold wrongly. Why did this happen? Whereas if you could come up with any number of amino acids, you would find that the many proteins fold less than a millisecond. Why aren't those part of our systems? Why did these get chosen, right? So that was the problem I was studying. My computer science peers were studying, forget about why things happen. Let's say that you give me a linear chain of amino acids. I want to build a platform that can very easily predict what is going to come at the end of X milliseconds, what's the 3D structure. Once I do this, people like Aruna, who are studying this boring problem, will pay me to use my compute to go study further on this problem, right? That's the insight that they started with. And turns out, although I finished my PhD before them, they were able to build things like AlphaFold and get much richer, right? So that's the first bad decision I made. Well, there'll be more, but this is the first bad decision. And I'm telling you so that you don't make such bad decisions again. I looked at it as, who cares for that platform? I'm going to study why this happens in one particular use case. I'm going to really deeply understand how to model why proteins fold. And they looked at whatever. It could be protein, it could be anything. I start from 1D, go to 3D. I'm going to do this repeatably. Okay, so we were looking for some fundamental interpretable, all those elitist things. And they were looking for practically who can, if a million people were using my system to compute things, what should it do, right? This is the tool we built. It was called NAMD, which is, I think, nanoscale simulations, molecular dynamics. The way it works is you're saying that between any two atoms, there are different kind of forces. There are forces that are electrostatic. There are forces that vary by bond, like you might have vaguely remember covalent bonds and all those chemistry things, like hydrophobic patches in a soap. So each of these mean that the atoms are binding together through different it takes a certain energy to break that bond or to move around in that bond. So if you go back to Newton and you look at every pair of atoms and you write down forces, and then you use that force and you propagate the system. Say at time t, I start with everything here. Now time t plus 1, I'm going to let every force act for a second or a femtosecond. I'm going to see where my system went to next. So that's the sort of code we contributed to. It's open source. People use it for studying dynamics of any biomolecules, anything which can be described by force fields. And we looked at what happens when a protein folds. Are there certain configurations that keep recurring, right? What does AlphaFold do? It says that I know already that a large set of proteins fold in a certain way. And I can see that they're all coded. They all start out having a certain code. If I just take similarities in these codes and I align similar things together, which is called multiple sequence alignment, I'm a little bit oversimplifying the techniques, but to give you the intuition for what they're doing. And if I use, here comes your transformer stuff on attention. Like if I pay attention to how these similar segments fold, I will be able to predict how a newer protein, which has only some similar segments to things that I know of, folds, right? So that's pretty much the approach that they took. And, that basically starts with searching for similar templates. An amino acid in a real human being has about, you might vaguely remember the ACGT kind of thing, and it repeats. So you look at where are these signatures the same. You try and embed your vector, your protein vector, in a way that these are aligned across your proteins. You do the usual covariance matrix kind of stuff, and then you get it to a place where you're encoding the protein. They call that evoformer. You're trying to capture relationships between amino acids that are similar, and you're trying to model both sequence and then where does it lie on the sequence. Similar to a LLM, which all of you know, looks at where in the sentence does a particular token occur, how is it related to other tokens. Very similar. And then they looked at, can I use a deep neural network to essentially predict where it's going to end up, right? And everybody uses it. It won the Nobel Prize. I'm here, and nobody I worked with won a Nobel Prize. So that's how, that's the difference between science and computer science. But turns out both are useful. My professor, who's not alive now, but would say that his group built a much better thing, because by number of users, science users, more users use molecular dynamics than people use AlphaFold. So I should say that. But what does it do better, and what are the trade-offs, right? So when you look at what the platform that a set of computer scientists built does very reliably, is given any new protein, it's able to come up with the end state, right? So if you're interested in, will this protein fold? Will it be functional? What's the time scale roughly of folding? You can answer those sort of questions on that kind of a system. What does molecular dynamics, which is basically looking at force fields and moving atoms, do? It basically lets you study the dynamics, meaning what happens intermediate. It may never, as it turns out, because you have a simplified reductionist force field, you may never, if you let, like my protein, which was a very small protein, about 300 atoms, took 3 months to fold in 2002 on a GPU, and that was the smallest. And so my advisor was fed up of me, as you can imagine, and he was like, don't run any larger proteins. It's done. Write your thesis with that 300 atom protein. That's more than enough for you, right? So the problem is that you often get stuck in local minima when you are optimizing force fields, and you may take a very long time to converge. Now it's been 20 years, so since 23 years, and now what took me 3 months might take 3 hours, but still, there's no guarantee that in 3 hours you're going to have a very large protein fold, whereas you're not going to run into that issue with AlphaFold. However, what you can study is that if I have a molecule that is targeting one particular patch on my protein, and I want to see where it attaches or what's the time scale of decay, it turns out that having a physics approach helps, because you can ask more reasoning questions around, let's say someone has a mutation that knocks off any C that comes after an A. Will this drug work for them? You're able to ask questions like that, which are harder to ask in AlphaFold, right? So that's why both are useful. So, and it depends where you are. If you're the slow burn, build for the long term. What did I start doing? I'm skipping over many things I did, but one of the first things I was assigned to was a problem where, it was our customer was in payments, and they were looking at obviously making people use more payments and spend more money. And their hypothesis was that, and Facebook was getting big around that time, 2007, 2008, and they said that, this was, let's say it's American Express, just for the sake of argument, and we want American Express to be popular amongst young people. And young people tend to spend together. So if you're popular, you tend to take out your friends to a bar, and in the US, people split the bill or at least pay for their own portions. So, you'd see a lot of transactions happen at the same time. So if you can actually find out people who are very social, obviously not scientists, maybe not even computer scientists, but more interesting people, they might actually be taking out newer and newer people every day to bars, to shopping, to wherever they go, right? And so can we find these people and target our rewards program to these people so that, we make more money out of every marketing dollar spent? This was the customer's problem. And it came down my way as like, okay, you seem to know some math, so figure out how to model this problem and figure out how to find them a list of customers they need to target to give them incentives. Okay? And this is like the US data for the scale is roughly about 30 million card members, and every day there would be roughly at that time around 1 million transactions per day, right? And we were looking at, so the way I started modeling it, I was an IC and I did my own thing, and I said, I'm going to model this as, we were only interested in physical stores, this is before too much online commerce dominated. And so you call something a point of sale. It's basically a place where you have a device where you swipe your card, and you'd look at transactions that co-occurred in a point of sale, and you said that, like, if you and I went to the cafe downstairs and bought coffee, then likely we know each other because we just bought the coffee together in time. It was hardly 2 seconds apart, right? And as you can imagine, there are many such coffee shops, and the more likely we are to have come together at every coffee shop, there's some signal that we know each other, right? But if we only co-occur in Ant's Cafe, it just might mean that we're in Indiranagar every evening, but we don't really know each other, right? So this was the underlying model that I went with, and I looked at two components. One is that the cafe itself has some natural, Poisson distribution of people coming in and buying coffee. So I'm going to model that. And then I'm going to say, given that we came within some time, let's say 1 second, and its average transaction rate average gap between two transactions is a minute, this is significant. Somehow we came before the rest of the queue together, right? So this is one signal. And the other signal is information contained in this signal. If we repeat this at other coffee shops, other retail outlets, then there's a stronger signal that we know each other, right? Or that at least one of us influenced the other into having that transaction. So this is how I modeled the problem, and I took it to production, and I wrote this code, and then I went and they were like, okay, when do we run this code? It's like, I don't know, I'm a scientist, I wrote this code, you run it whenever you want, right? So my deliverable is over. And then I figured that actually that's not how the marketing team wanted it. What they wanted was that every day at every point I have a budget. Marketing budgets came every day. So today I might have a budget of $10, tomorrow I have $20. And the way these budgets work is that I have to burn today's budget today. I don't get to carry it over, right? So it's like reward points a little bit, they expire. So they want to know right now, who do I give something to? And there's no time to like say that I'll look at previous data and I'm going to come up with some sort of average distribution on a particular coffee shop. And then you can imagine that that will change every day, that will change, it'll be different 2 years ago versus now. You can imagine that, these points of sales, some shops will shut down, some new shops will come up. So your code has to handle all of this finally in production. And it turned out that that was the first time I worked on the same problem with a computer scientist, not just to do a PhD, but to actually ship something within a week. And the way they looked at this problem, they were from a machine learning background. They said, okay, let's forget about all your math. Let's just say, let's use information, and let's say that any two people that co-occur at a point of sale, we'll call them friends. We'll give the first one a voucher every day, right? And then we'll run a job that actually looks at, you just make a graph this way, add an edge for every two people that come right after each other. And then you, at the end of, let's say 6 hours, you drop nodes that are not contributing to the information in the graph. You understand the notion of information minus P ln P. And your P there is looked at as the probability that you would come together across one point of sale, me and you. And assume that every point of sale in Bangalore is equally open to us. You geographically restrict it, and then you say, if we only peak at one place, if we didn't come together at all, obviously there's no information contained in our edge, just drop it. If we came together only in Indiranagar Ant's Cafe, likely we just work there or something like that, drop it. So it's like a spiky distribution, right? Either 0 or 1. And anything that is more uniform is more stronger signal that we actually occurred together. So you don't need to think about it in that way. You just look at minus P ln P, and you keep trying to minimize this, right? And you keep saying that I'll only keep edges at the end of the day that are contributing to information content or minimizing entropy. So it suddenly opened my mind to, okay, the real world works this way. I should learn how to start coding, using more MapReduce, using more production systems, figuring out how do I plug in, how do I live with errors? Like if I don't have a point of sale sending me data, I should still take a decision in my code on give a coupon or not give a coupon, right? So There are more and more things to model if you look at it as a reductionist problem. If you look at it as an ML problem, there are less and less things to model and more things to compute. You don't care, you just take a point decision and you record it. And every day you look at your log and see how much money did I give out in offers and how much did I make back. As long as that, is above the marketing threshold of what's acceptable, you keep running your thing. And it's a pretty low stakes experiment in that, like, what's the worst? You and I get a coupon and we don't know each other and we find out that now we know each other, right? Great. Or we never know each other, it's totally fine. It's not a very high stakes thing where, you need to have a reductionist model of what's going on. So that sort of opened my mind, and I realized that there is a lot to learn. So, then people got excited and they said, we had VPs and SVPs, all these bothersome people. And the SVP said, okay, we're paying scientists. We were paid very less. We came from academia, but still it was quite a lot compared to people sitting in a call center and taking calls and making judgment on whether to give a customer an offer or not, right? So with all these expensive people, can I change the way that I model credit, right? So conventionally, a statistician, economist, even a natural scientist getting into credit will look at credit as, how should I model your credit history? I should look at 2 or 3 parameters. I listed out 6, random number. There were many more than this, but let's say I am, let's say, Paytm, and I know how often you borrow from me and you pay me back. So I have your payment history. I know how you pay other people. I know your outstanding debts in some sense. You've let me access your CIBIL score and your credit history. So I know that you owe a bank, let's say for your house about X crores if you're in Bangalore, right? And I know the length of your credit history. When did you first get an account with Paytm, and when did CIBIL first open a score for you, right? Similarly, I know, I know what types of credit you've used, credit card versus Paytm versus a bank loan. I also know how much credit you actually use. Like your credit card might give you up to a 10 lakh limit for spending, and you might actually only be using 2 lakhs, or you might be maxing out and using 20 lakhs, right? So I have some sort of utilization there. And again, physics people learn very slowly. Except you, we have a very small learning rate. So we don't leave our habits, right? So I looked at this again as a reductionist problem, and I said, okay, I'll model your credit score by doing dimensional analysis across these and making sure they all work out to cancel each other, and it comes to a score. So, money by money is a number. I looked at it this way, and I made a new model for credit scores. Obviously, there were smarter people that said, what if we applied, attention to this? It was not exactly attention at that time, but think I'm just modernizing the problem. We did something with Bayesian method, but let's say we are able to use Paytm today will pay you for this. They're hiring data scientists who basically go in and say, we look at all the payment, and then we just say, we are trying to predict a number of what loan to give this person. And every payment in is positive, every payment out, like money taken out of Paytm is negative, and that's all I need to know. And I take the CIBIL credit score, I take everything else that I'm taking from your credit score. Actually, it's FICO, I think, yeah. I don't know why I'm saying CIBIL, but whatever. I take that, and then I try to predict what is your limit of spending, right? And now new business models have come up like this, where people actually are giving loans separately from banks, right? Like, I'm fast forwarding a bit. My story is boring, so I'll go to a more interesting story. Like if you have Navi, you have all of these new fintech companies, and why are they doing well in India? Because a lot of people want to start businesses. We were told that we have to do chai and pakoda, so we are taking it seriously. Every day we are trying chai and pakoda. We need money, right? We don't sell enough chai every day to have money to make chai the next day. So we need to borrow from somewhere. And this is a massive problem in India because employment rates are low. Very few people actually go out and work for other people. Most people are trying things where they're doing small business. So they need a lot of credit, and they don't have a great credit history. So if you look at number of these people that get bank loans, it's very, very tiny because they don't have the conventional assets a bank looks for. A bank takes a very reductionist approach. Okay, if all of these are zero, I know nothing about you. So no, I'm not giving you a loan, right? Unless you're related to Nirav Modi, that's completely different. Then I need to know nothing about you and you can take my bank. But if you're not that and you appear at scale, then basically I know nothing about you, I won't give you a loan, right? And most people are people we know nothing about. So turns out banks are leaving some money on the table in terms of, I might be a good business person, like your vegetable vendor. Every day she borrows 1,000 rupees from someone. She buys vegetables for 1,000 rupees. She sells, she pays that person back 35% interest at the end of the day, right? And sometimes she pays at the end of the week, but she's still able to make money by paying that. You can argue fair or unfair, but this is how pretty much the entire country is working. So if you're able to actually just look at how many people buy vegetables from her, you should get an idea of, is she worthy of giving a loan or not? And this is how all of these new age companies have come up saying that you don't need to have a house or a car or anything. Just open your app every day and pay with Navi UPI or Paytm UPI or whatever, and RBI willing, you will get a loan from us. Or the other way, you can say that whenever you have a limited amount of data and you're trying to use that to make a prediction, even if you're using ML, you're increasing the risk in your business model is inherently more risky. And you have no way to quantify this risk because you can only benchmark it against the lowest risk people like banks. So you're taking more risk. And how our businesses started hedging this risk is to have collection agencies. So the reason RBI shuts down these businesses every now and then is because they hire collection agencies who, are not very nice people. They don't just call you and you keep changing your SIM. They actually come to your house and try to threaten you, socially shame you and all of that. And that's how the company is going to make back money, right? So pretty much that's how a large amount of fintech works. And sad story, but it's true. And that's how, that taught me a little bit about the decision on whether to do this has to be taken upstream. You can't at this point in time say that I'm going to instrument more data or I'm going to have a hyperparameter that I can tune that decides whether to give a loan or not give a loan. I need to actually go back and question my business model of giving loans, and I need to look at how much loan am I ready to give, what should be my payback rate, and if I need to do this without engaging a collection agency or engaging an ethical collection agency, whatever that be, how would I do this more responsibly? So you can understand that I'm just trying to motivate that this is not an ML problem alone. Like you're not going to fix this by buying a GPU and looking at these things as hyperparameters. You'll have to go and look at how do I lend money? What kind of risk am I ready to take? And it's totally okay if at that point in time you say I'm okay with vegetable vendors but not okay with people who sell coffee, and you make that an if-else statement in your code, that's totally okay, right? So you should be able to make these decisions in a business at a fast pace to run a business that's up and running, making reasonable decisions and not overshooting the amount of risk you're willing to take. And some of this is not quantitative, some of this has to be done every day. And that's when you learn, when you get into managerial roles, you learn how to take these decisions with very incomplete data, with very, very good scientists working on the models, but still you decide, no, I won't go with the model, right? So this is sort of growing up. So this was Myntra. We were looking at, I was older by this time and I had a larger team. And so the stakes went up, like basically I can't put my team members on the wrong problems, right? And and fashion is the most polluting industry after oil and gas. About 70% of, that's the minimum. Minimally 70% of things that you make end up in oceans or landfill and eventually seep into oceans and kill dolphins and stuff like that, that your 2-year-old will be shocked at, right? But could we do better at predicting this demand is pretty much what every fashion company CEO thinks about. And this was 2016-17, and they were looking at, okay, now, ML is a mature field. Can you reduce my wastage, right? And this is the problem. Forget the equation. It's just that's demand for an item I at time T, and M is merchandising parameters, price, brand, blah, blah, blah. D is derived parameters, seasonality, etc., etc. What's the problem? Because fashion is an industry where you need to carry a long tail. Like even though you'll find that 20% of my inventory is what 99% of the people are buying, if I cut out the rest of my 80% inventory, nobody will buy from me because I'm looked at as, I don't know, some shady person who's just having 20 t-shirts on sale. I really need to have 2,000 t-shirts on sale for people to buy the same 20, right? That's how business works. So, and that's how fashion business works. And those large, long scale, long tail, 2,000 extra t-shirts that I have to keep changing so that people perceive me as someone who is actually keeping up with time, not like, some lazy engineer who just printed out 10 t-shirts and is sitting with a store just running that, right? Even those 10 might be really popular t-shirts, but still people are going to stop buying from me. So in this sort of a situation, can you build me models to basically predict much more accurately than my category managers are predicting? They're using a combination of Excel, their own brains, which they have much more than us, and they figure out what to buy, what not to buy, what to list, what not to list. And now can you do better than them? Okay, this is the problem. We tried, okay, I had a larger team, so we tried different things. We tried XGBoost, we tried, at the time, transformers had just come out. So we tried, a transformer-like thing, but with RNN and fully connected layers. We tried CNNs. And although there is a lot of literature that says that for time series data, CNNs plus FC layers do the best. That is benchmarking against very known time series open source data. Your own time series data may be different. And what we found is that XGBoost did the best, and these other models came nowhere close. Given whatever limitations we have the data we have, and you can't get any more data than you have, and all of these are now libraries, so there are no implementation errors. So, what went wrong? Basically, on that data set, our RNNs or our CNNs were not able to pick up any more temporal trends than we were able to model into an XGBoost with, say, a derived feature like seasonality, cannibalization. Some of these handmade features made a bigger difference, right? Which is more expensive, more time spent by your data scientists to do this, not as elegant, cannot publish paper. We published anyway, but forget the model architecture. So that's the moral of the story. And then we did better than existing people existing category folks by creating a bunch of features like number of other styles listed in the same week, comparable brands, blah, blah, blah. And we were able to get incremental lift. Again, I said I'll tell you when people get carried away. So there are people called chief product officers, chief dreamers, chief visionaries, right? These folks say that, okay, I have assets in my company. How do I use this to raise the next $1 billion? And then they came up with, hey, I read papers that say that you can now look at an image and say what's going on, say what's on it. So you guys know CNN, you know feature extraction, you know that if I looked at social media and I followed the Paris Fashion Week, I can say what's selling, right? Somewhat. Can you just crawl the entirety of the internet, whatever it is, whatever that means to you? And then they came up with this idea that also we separately on our research side showed that you can use GANs for image generation. Never mind that, but can you now just generate me images of fashion that will surely sell? Like, that this is the kind of things that CEOs come up with. Sometimes it's very hard. Like sometimes you say they are geniuses, sometimes you say they're foolish, and the line is very thin, like Musk is demonstrating, right? So this is a problem they gave us it didn't really help being head of data science or anything. Turned out that's just a middle layer. Can a program basically generate fashion that sells? It should not sell. And then tell me how many units to make. Obviously, it sounds like a Bejan Daruwala kind of problem where someone's coming to you and saying that, Guruji, please tell me exactly what to make that will sell, right? And then you know that you should not sign up for this. So that's when I left. But apart from that, this is like a clear snake oil problem where you are extrapolating the fact that you got lift in your demand prediction errors to, like, you can perfectly always estimate demand and at least cut away. And you can use the fact that you can generate and you don't need any humans, and you think that the loss in this is coming from humans interpreting. Like when I generate a certain demand forecast, I'll say t-shirts, half sleeve, red color, right? But there are many ways to make a t-shirt half sleeve red color, right? And a designer has obviously some room for thinking on how to make a t-shirt half sleeve red color. Is it half red, fully red, blah, blah, blah. And you think your errors come from there. And ML is very good. So if only I didn't have a designer in the loop and I fed this to a GAN and said, make me a t-shirt half sleeve red color, I'll somehow sell more. Okay, so this was, people make these hypotheses, and then a lot of real world skill is how do you negotiate through these hypotheses and how do you make sure you're not falling into a snake oil trap. I think I will end with that. Thank you. Any other questions?